Welcome to this explainer. Okay, so today we're going on a pretty fascinating journey, and we're actually going to use a botanical metaphor to guide us. We'll start with just a single seed of data, grow it into a branching machine learning tree, and eventually cultivate an entire, highly powerful predictive forest. If you are looking to really grasp how some of the absolute most widely used machine learning models actually work under the hood, you are in the exact right place. Let's dive in. In today's tech landscape, the hype is everywhere. It's so easy to just assume you need a massive, power-hungry neural network for absolutely everything you do. But honestly, when it comes to the kind of everyday tabular data you'd find in a standard spreadsheet or a SQL database, is a complex neural net really the best tool for the job? Think about the Palmer Penguins dataset, for instance. This data is the perfect seed for our models. It's got this great mix of numerical features, like bill length and weight, and categorical labels, like the specific penguin species. Essentially, it's everything you'd ever want to know about a penguin. And this is the exact kind of structured row and column data that businesses, researchers, and data scientists rely on every single day. So here's our roadmap for this explainer. First, we'll talk about why this is the tabular data solution. Then we'll grow a decision tree, tackle overfitting, plant a random forest, and finish up with gradient-boosted trees. All right, section 1, the tabular data solution. Let's see why decision forests are literally built for this kind of work. The absolute best part here is that unlike neural networks, decision forests let you just skip all that tedious pre-processing. You don't have to normalize your features. You don't have to stress over one-hot encoding. They natively consume tabular data exactly as it comes. Plus, they're incredibly sample efficient, meaning they perform incredibly well even if you're working with a pretty small dataset. You can feed them raw, unnormalized spreadsheet data, and a medium-sized forest will spit out an inference in just a few microseconds on a standard CPU. It is a straight shot to lightning-fast predictions. Moving right along to section 2, growing a decision tree. Let's look at how we build this from the root up. Now, these models function exactly like a flowchart, which makes them highly interpretable. But actually, scratch that real tree analogy for a second, because unlike a real botanical tree that grows upward from the ground, decision trees are modeled with the root at the very top. So an example comes into that root node, answers a series of true or false conditions, like say, is the bill length greater than 16 millimeters, and gets routed all the way down to a leaf at the bottom. And that leaf holds our final prediction.
But how exactly does the tree know which questions it should be asking? Well, to mathematically find the absolute best split at each node, the algorithm calculates something called information gain, and that relies heavily on minimizing Shannon entropy. Think of Shannon entropy as a measure of disorder, kind of like a messy room. If a node is an exact 50-50 split of Adelie and chinstrap penguins, that room is completely messy and entropy is maxed out. But if the node contains only one species, the room is perfectly clean, perfectly pure, and entropy is 0. The whole goal for the algorithm is to find the split that reduces that messy disorder the most.
Using that math, the algorithm goes all in on a greedy divide and conquer strategy. It starts right at the root, evaluates pretty much an infinite number of possible numerical thresholds, and finds the single best immediate split to maximize that information gain. From there, it creates 2 child nodes and just repeats the whole process recursively until it simply cannot find any more satisfying conditions. Those final, unsplittable nodes, those become our predictive leaves. Which brings us to section 3, dealing with overfitting. Because as that tree recursively grows deeper, we run into some issues. Specifically, the tree can become wildly specific to your training data, but tweaking just a single hyperparameter physically alters the entire structure of the tree. Let's say we set the minimum number of examples per leaf to just 1. Well, the tree is going to keep splitting until it perfectly categorizes every single training example. That creates a massive, sprawling, deep tree that essentially just memorizes the noise in your data. And spoiler alert, it'll perform terribly on new, unseen data. But if we increase that hyperparameter to, say, 5, we effectively prune the tree. We keep it broad, generalized, and a whole lot more accurate out in the real world. And because a single decision tree is so transparent and interpretable, we can easily extract variable importance scores. These act like a diagnostic X-ray for our model. If a feature, like bill depth, is constantly being used to make really high-value splits, it gets a high importance score. On the flip side, if a feature is almost never used, we instantly know it's not really contributing much to the model's overall intelligence. Okay, zooming out now for section 4, planting a random forest. Time to take things to the next level. Since a single tree definitely has its limitations, we ensemble them.
By training multiple independent trees and intentionally injecting random noise, we build a highly robust model that actively resists that nasty overfitting trap we just talked about. This uses a technique called bagging, where every single tree is trained on a randomly selected subset of the examples. Once the whole forest is grown, they all look at the new data together and basically just take a majority vote to arrive at a final, incredibly accurate prediction.
And this naturally brings us to a super clever built-in trick: out-of-bag, or OOB, evaluation. Because of that bagging process, each tree only ever sees about 67% of the training data. This means random forests don't even need a separate validation dataset to check their own homework. To test the forest on, say, example 1, the model simply asks for a prediction exclusively from the specific trees that never saw example 1 during training. It's an elegant, highly efficient self-validating system. Finally, section 5, gradient-boosted trees. Let's look at a totally different way to build our forest. So, gradient-boosted trees are a whole different beast compared to random forests. While random forests train tons of deep trees independently and in parallel, gradient boosting leans on a sequential, error-correcting methodology. It kicks off with a strong model, which honestly initially might just predict 0 for everything, and then it iteratively trains small, weak decision trees that are specifically designed to predict and correct the mathematical errors of that initial strong model. Now, this little decimal right here, 0.1, represents something vital: shrinkage. Shrinkage acts exactly like a learning rate does in a neural network. Before one of those weak, error-correcting trees is added to the main, strong model, its predictions get multiplied by this small shrinkage value. This purposefully slows the learning process way down, carefully controlling how fast our strong model learns from the weak ones, which keeps it from wildly overcorrecting. Let's actually demystify how this boosting mathematically scales and improves step by step. First, the model looks at the gap between its prediction and the actual label. This gap is the gradient of the loss, or the pseudo-response error. The new weak tree then learns to predict that exact specific error. Its output is scaled down by the shrinkage, and finally, it's merged into the strong model. Step by step, iteration by iteration, the total error is just relentlessly driven down. What's really fascinating here is that advanced calculus is secretly running the show behind the scenes. While basic gradient descent just uses the first derivative of the loss function, gradient-boosted trees often bring out the big guns, Newton's method. By incorporating both the first derivative, the gradient, and the second derivative, the algorithm can incredibly accurately optimize the final mathematical values sitting right there in the leaves of our trees. It makes the entire forest vastly more precise. But, and this is a big but, unlike our random forests, gradient-boosted trees absolutely can and will overfit if you aren't careful. Because they are sequentially and obsessively chasing down errors, if you let them run for too many iterations, they'll just start memorizing the noise. That makes early stopping and having a separate validation dataset strictly necessary. You've got to watch that validation accuracy like a hawk and halt the training the absolute second the accuracy begins to drop. You know, the documentation really hits the nail on the head here. Despite all the complex math we've talked about, Shannon entropy, Newton's method, happening under the surface, these models remain the undisputed champions for tabular data. They are incredibly robust, they completely skip the headaches of complex data preprocessing, and they run at blazing fast speeds right out of the box. So, we've gone from the raw mechanics of a single little decision tree all the way up to the heavy-hitting error correction of gradient boosting. The structured rows and columns sitting right now in your spreadsheets hold immense predictive potential. The question is, how are you going to apply this knowledge to unlock the insights hidden within your own tabular data? Thanks so much for learning with me on this explainer. See you next time.